Right, hello everyone, I'm Atreya, and as Luke mentioned, I'm here to talk to you about the discoveries that shaped our understanding of the universe and where I fit in. So let's see if I get to the next slide. Hang on, I can't get to the next slide. Yes, there we are. So hello again, I'm Atreya. I'm a final year PhD student in gamma ray astronomy. What that means is I look at faraway galaxies like that and try to figure out where the most energetic light particles, as in the gamma rays, are coming from. More on that later. When I'm not doing that, I also tutor first year undergrads. If you're one of my tutors, hello. I'm also privileged enough, as Luke mentioned, to be a college mentor at Castle. So you might be one of my mentees. So there you go. Those are the pictures of all my mentees. So if you are one of my mentees, hello again. I really miss you, and I really hope we can again soon meet up and organize loads of events and loads of formals. So fingers crossed for that. We're not doing either of those. Other hobbies include walking up hills. Okay, so there's a picture of me at Yosemite a couple of years ago. I play the piano rather badly, and I like watching football. As you can guess from the picture on the right, I'm a Tottenham Hotspur fan, and I'd rather not talk about it at the moment. You know, I know we have a few Arsenal fans in here. Let's not talk about it. I'll leave it there, let it linger, and make of that what you will. Okay, so moving on to the next slide. So, prologue. So I thought I'd do something a bit different to begin with. So instead of talking about my research, which I promise I will come on to at some point, I thought, let's take you back in time some 500 odd years. Why not, for a start? Okay, so Durham Castle was around back then, because of course it was. Just putting it in there, Hatfield wasn't. I don't know why I mentioned it, but I thought I'd just put it in there. Durham Castle was around, Hatfield wasn't. Just leave it there. And the people living in Durham Castle back then believed that they were the center of the universe. Not just them, pretty much everyone living back then believed that they were the center of the universe. And the reason they did so is because people believed in Aristotle's universe. So in Aristotle's universe, the Earth is at the center of the universe, and all the planets and the sun move uniformly around the Earth. That's what they believed in. I know it's strange, but that's what they believed in. Furthermore, they believed that the stars were all fixed. So that's what they believed roughly 500 years ago. Okay. However, Mars started acting a bit funny. So what would happen is, you see, Mars would, while on its course of its orbit, would suddenly stop, turn back on itself, and then keep on going. As you can see from the animation, it'll stop, turn back, and keep on going. So I'll sort of do a loop-the-loop, so to speak. Okay, and this loop-the-loop behavior is called retrograde motion. Okay, this is what people observed. And this retrograde behavior made absolutely no sense, because why would it suddenly stop and then go back and keep on going? Okay, and when something makes no sense, we as human beings in general, and scientists in particular, question that something. So it made no sense, and then hang on, why is that happening? So luckily, there was a clever young man in Poland who did just that. His name was Copernicus, and he came up with the heliocentric model. So under the heliocentric model, all the spheres surround the sun as if it were in the middle of them all, and therefore the center of the universe is near the sun. Now, as we know now that this is not strictly true, okay? The solar system is nowhere near the center of the Milky Way, let alone the universe. So the sun is definitely nowhere near the center of the universe. However, back then, this represented one of the greatest leaps we'd ever done in science. Before then, we believed the Earth is the center. Copernicus was the first guy who went, hang on, maybe the sun is in the center. Okay, so even though it's still wrong, it still represents excellent progress, the best progress we've made till then. And this sort of relates into what you might find with your own investigations. Okay, well, whatever stage of your own scientific careers you're in, very rarely do we get to the correct answer in one go. Usually, learning and also life in general is a step-by-step process. And as long as you believe in the process and keep on plodding on, you'll be fine. It took them 2,000 years to figure this out, so you're doing very well for yourselves, so don't worry. So there you go. That was Copernicus and his heliocentric model. I now move on to Galileo. So in 1610, Galileo observed for the first time ever the 4 moons of Jupiter. Okay, and the reason why this discovery is important is because this was the first proof of celestial bodies orbiting something other than the Earth. So till before, as I mentioned, people believed that the Earth was the center and everything orbits the Earth. But as soon as Galileo discovered celestial bodies orbiting Jupiter, as in orbiting something other than the Earth, people got very excited and go, hang on, maybe we're not that special positionally. Positionally speaking, the Earth really isn't that special in the grand scheme of things. In other ways, we are, and I'll come on to that later on in the talk. But positionally, we aren't really that special, and Galileo's moons of Jupiter really helps point that out. The next discovery I'll talk about is Herschel. So in the 1800s, William Herschel counted, yes, counted all the stars to form a map of the Milky Way. So he counted all of them. Now, while his map was of course wrong, because firstly, you can't see all the stars because they're either below the horizon or they're covered by dust, so you can't really see them. And even if you could see them, counting all of them is incredibly difficult. So his map was of course wrong. However, he did reveal the Milky Way to be a lot larger than previously imagined. And furthermore, he revealed that the sun was nowhere near the center. So once again, we haven't got to the correct answer yet. However, Herschel, just by counting all the stars, has revealed 2 significant discoveries, which are still true today, because we know the Milky Way is really, really big, and the sun, as we'll see later on, is nowhere near the center. So this was in the early 1800s. And then sadly, this is where we stood for the better part of a century. So back then we had peaks and troughs. So after this, we entered a bit of a lull period, of a dark ages when it comes to science. So basically not much happened until almost 100 years later, when a certain German bloke got bored of his day job. You might have heard of the German bloke. His name was Albert Einstein, and he came up with a theory of relativity. Now, right at the start, I want to caveat all this by saying that relativity is one of the most incredibly interesting aspects of just science in general, right? And to be honest, it deserves its very own talk. You know, there's no way one slide can ever do it justice. So hopefully one of these talks you will hear someone talking about relativity, but in my own small way, I'll try to summarize the key points on this slide. So it comes in 2 flavors. You've got special relativity and general relativity. So special relativity. What it says that as long as an object is moving at a straight line at constant speed, i.e. no acceleration, the laws of physics are the same for everyone. So as long as it's moving in a straight line, constant speed, same laws of physics. This follows on to the second point, where we say that light travels at an unvarying speed of 3 × 10⁸ meters a second, regardless of the motion of the observer. And this, I think, is an incredible point, because usually motion is all relative, right? So imagine you're at a tube station going up an escalator at the tube station. Your net speed would be your speed plus the escalator speed, right? Now imagine if you're going down an escalator going up. So you're going down an escalator going up. Health and safety, not a good idea, so never do this. But if you did, your net speed would be your speed minus the escalator speed. It's all relative, hence the word relativity. However, this is not true for light. Okay, for light it's different. Light is constant in vacuum. So imagine if I held a flashlight and I was running. Okay, as you can guess, I'm not very fast. But if I held a flashlight and I was running with it, and if Usain Bolt, who is potentially 1,000,000 times faster than I am, held the same flashlight and was running, the speed of light from our flashlights would be the same. The speed of light from our 2 flashlights would be the same. It doesn't matter the fact that he's 1,000,000 times faster than I am. It does not matter how fast the observer moves. And that is incredible. Okay, that's why I think special relativity is one of the most incredible things ever discovered. Also, we have general relativity. Okay. So the main idea is quite simple. Gravity curves space, and the more massive an object is, the more it warps the space around it. So to give you an example, imagine you and a mate have a bed sheet and you've held it on 2 sides, and in the center of the bed sheet, you put a dumbbell, a couple of dumbbells. So what happens is because of dumbbells, because of the weight of the dumbbells, the bed sheet has a dent, okay, or what we call a warp. And therefore, anything if you put around it, it finds it difficult to escape, okay? And also, as you can guess, the more massive the object, or in our case, the more massive the dumbbells, the more it bends or warps the space around it. And this, very crudely, is the principle behind black holes, okay? So regarding black holes, I will tell you now, you guys have already seen at least one instance of a black hole already this morning, okay? If you don't believe me, go back to when you were brushing your teeth. I hope you all brushed your teeth this morning. It's a good idea. When you brush your teeth, the water going down the sink, okay? The water near the sink was moving fast. The water further away was moving slow. Similarly, when objects rotate around the black hole, the objects near the black hole move fast. The objects further away move slow, and when these objects moving fast and slow collide with each other, it leads to friction, which creates thermal energy, which you see as a thermal emission, the thermal light at lower energies from these objects. There's also another kind of emission, but I'll come on to that later on. So for now, that very crudely is the principle behind black holes and relativity in general. The next discovery concerns Edwin Hubble, who discovered the expanding universe. So in 1929, Edwin Hubble found that galaxies are all moving away from us. Furthermore, the ones further away are moving faster. You know, it sounds like me when I hit the dance floor at Clute, all the girls move away from me, and the ones furthest away basically run away, you know, just like that. All galaxies are moving away from us, and the ones furthest away are moving faster. The reason this is important is because this was the first evidence we had that the universe is expanding. Now, that's interesting. The reason that's interesting is because it means if something is expanding, if we then take it back in time, it means to begin with, it started out small. It started off very, very small. It started with a bang, the Big Bang. Okay, that's how all of this happened. All around you, started with a big bang. I'll come on to that at the end of my talk. Okay, so in Durham, we are lucky enough to have the ICC, which you might have heard of, the Institute of Computational Cosmology, who basically simulate the universe as it was right at the start of it, right at the Big Bang, a few milliseconds in. And there's some enormously impressive work where they simulate the conditions as they were right at the start, just after the Big Bang. Now, sadly, we don't know the exact story yet, so no one knows exactly what happened. We're still in the process of figuring things out. We're very close to figuring things out, so probably in our lifetimes we will, but for now, no one knows the exact story. Now, you might think that to be a bit lame, you know, so, I mean, what's the point if you don't know, you know, what's the point of doing all this? Well, I disagree. In fact, I think the fun in science in general is in the not knowing. I think that's where most of the fun is. If you don't believe me, I'll give you an example. I'll take you back to Valentine's Day this year. Okay, when your significant other gave you a nice gift wrap present, and then you're all excited to figure out what it was, and then you went home and you opened it, and then you found out that it was something you neither want nor need, and you felt a bit sad. So there you go. The fun is in the not knowing. Speaking of not knowing, I wouldn't know because I did not have a Valentine this year. So if you know anyone who might be interested, put a word in for me. Who needs Tinder when you've got DUPS seminars? And I wasn't supposed to say that, so I move on very quickly to the next slide. The next slide concerns cosmic microwave background. So a couple of astronomers, Penzias and Wilson, actually discovered this, and this is believed to be leftover radiation from when the universe was at its very earliest stages of growth. Okay. And the reason this is important is because it offered further evidence in support of the Big Bang theory. Remember the earliest stages? Okay. Now, the idea is that this radiation has been present since the Big Bang and has spread out as the universe has expanded. And on the right, you can see a sky map of what the current cosmic microwave background looks like at the moment. So there you go. So by studying this cosmic microwave background, we can understand what happened right at the start, and I'll come on to later on where my own work might fit in helping us do so. But for now, that is what cosmic microwave background is in a nutshell. The next discovery I'm going to talk about is extrasolar planets. So in 1995, a couple of Swiss astronomers, Didier Queloz and Michael Meyer, discovered the first extrasolar planet, Pegasus B. The reason why it's so important is because since then, nearly 4,000 extrasolar planets are now known to exist. They're discovering them every day, so that could be out of date, to be honest, but they're discovering loads and loads of solar planets, and that's really interesting. That's interesting because of this. If there are planets, there may, just may, be life. Okay. Now, I know it's hard to believe, okay, given the talk I'm giving, but I actually do this professionally. So part of my day job is I go to schools up and down the Northeast. We have a planetarium, which looks like a bouncy castle, and I project the stars onto it and show the kids all the constellations. I know it's hard to believe, but it's true. And the one question they always ask me all the time is, are there aliens? And I sort of address that from a scientific point of view, so I might as well. Okay, so here's the problem. We're scientists. We believe in evidence. So far, the only evidence we have of life is on Earth. And the only evidence we have of what we require for life is water. So searching for life, in this case, is certainly equal to searching for water. Now, why do we exist? It's because when the solar system was formed all those years ago, by some fluke, when it was formed from the collapsing cloud of gas and dust, by some fluke, and we have no idea what fluke, the Earth was formed at exactly the right distance away from the sun, not too close and too hot, not too far or too cold, exactly the right distance so we could support liquid water. So we could have temperatures between 0 and 100 degrees centigrade and therefore host liquid water and therefore host life, and which is why, by some fluke, you and I exist and you're having to suffer through my talk. So sorry about that. So yeah, we are in the habitable zone or the Goldilocks zone by some fluke. Okay. So as I said, so when we are searching for life out there, what we're doing is we're searching for other planets which would also have temperatures between 0 and 100 degrees centigrade and therefore potentially host water. And if they potentially host water, they could potentially host life. So are we the only lucky ones? Well, there are a million galaxies, each with a million stars, each with millions of planets. So if you do the maths, if you add it all up, the chances of there being another planet out there, just like us, who could potentially host life, they're not zero, are they? They're not zero. So I'll just leave that there and let you think about that. Are we the only lucky ones? For now, yes, well, as far as we know, but potentially that could change. But as I said, I'm in no way saying that there are aliens. I didn't say that. I now move on to the next discovery, which is the NASA Voyager space probe. Okay, so the Voyager program launched by NASA, as you can see in the top right-hand corner, studied all the planets in the solar system and has now gone beyond it. Okay, now the cool thing about it is it reveals all our planets in glorious detail. So on the bottom right is an enhanced photo of my favorite planet, Saturn. If you're wondering why it's my most favorite planet, it's because of the rings, obviously. And the cool thing about Voyager, the reason I mention it is because on the 14th of February 1990, Valentine's Day again, Voyager 1, from about 6 billion kilometers away from the Earth, took not this brilliant picture, although it is a brilliant picture, but instead took this brilliant picture. So this picture you see over there is the pale blue dot picture. So this is what the Earth looks like from 6 billion kilometers away, so far, far away. That's all we are, a pale blue dot. And this, to me, is one of the most amazing and mesmerizing pictures ever taken. Not just in astronomy, ever taken. That is the most incredible picture, I believe, that was ever taken. Okay, now, I remember being a young teenager back in India when I first saw this picture on the back of a magazine. And once again, to be honest, if it weren't for that picture, I would definitely wouldn't have been an astronomer. So thank you. I really love that picture. Now, I could go on talking to you about this picture till kingdom come, but you don't want to hear that. You probably get bored and leave the meeting. So instead, what I'm going to do is I'm going to read you the words by someone who knew a lot more than I ever will. That certain someone is called Carl Sagan. You might know him. He had a TV show called Cosmos on telly. He's also a famous American astrobiologist. He's basically Brian Cox before Brian Cox. So he saw this picture and he came up with the following passage, which I'll read. And I'll try to get some music in. So apologies for the poor sound quality. That might be a Zoom thing, but let me know. Hopefully it's not too bad. So let's see as I read this out. Look again at that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of. Every human being who ever was lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines. Every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on a mote of dust suspended in a sunbeam. It has been said that astronomy is a humbling and character-building experience. There is perhaps no better demonstration of the folly of human conceits than this distant image of a tiny world. To me, it underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we've ever known, which to me is remarkable, by the way. So to me, that is the most remarkable picture ever seen, and who am I to argue? Okay, now just by looking at the picture, look at how small we are. You might wonder if, if being so small, being just a dot, somehow makes us insignificant. Okay, to put that in more perspective, you look at the picture on the right. So on the picture right, you can hopefully see what the Milky Way looks like. Okay, so what we think the Milky Way looks like, of course, is an impression, not an actual photo. And that arrow pointed over there is where the solar system is. That arrow points towards the solar system. And we are, in fact, in Durham, in the United Kingdom, still somewhat in Europe. Let's not go over there. Okay, in a planet in that solar system. We're in one corner of that tiny corner of our universe. Okay, so we are really small. However, the reason I disagree with that making us insignificant is we as human beings have evolved to such an extent where, despite living in one tiny corner of a tiny corner, we as human beings can not only explore all of that and beyond, but we have progressed to such a level where we can understand and comprehend all of that and beyond, which to me shows that we are the most significant, insignificant people who ever lived. So there you go. I just told you human beings are special. You can have that for free. And we can do that because we can study the universe around us and all the other galaxies. Now, speaking of other galaxies, this is where I somehow fit in. So as you might remember, way back at the start, I said that I'm a gamma ray astronomer. Okay, so it's a cool gig. I would highly recommend it. You can do some really cool stuff. For example, last year, I had the pleasure of going to NASA and giving a talk over there, which is super fun. I do regret being a bit hungover when I gave that talk, but they invited me back this year. So I don't know, maybe they like that sort of thing. But no, the cool thing is you can go to telescopes, visit, and then observe the universe from these great places. So I really enjoy that. Okay, the other really great thing about being a gamma ray astronomer is you get to work with some really amazing people. So on the left, you can see what are my work family, my gamma ray family here in Durham. So for example, in the top left, we have Professor Chadwick, my supervisor, my boss. You might recognize her as a lecturer. She's basically supported me throughout my entire PhD and another lot. Next to her is Anthony Brown, my other supervisor, who's also helped me out a lot, and basically he's taught me most things I know. Next to them is Dr. Alton, who's a postdoc, who's also helped me, especially settling in, getting the softwares in. And in the bottom panel, from left to right, are Max, Sheridan, Alberto, my fellow PhD students. I'm also very lucky to work with and share ideas with. So what exactly is gamma ray astronomy? Or rather, what are gamma rays? So gamma rays are at the extreme end of the spectrum. So you remember the electromagnetic spectrum, we go from radio waves, from microwave, infrared, visible, ultraviolet, X-ray, and then ultimately the gamma rays. So gamma rays have the shortest wavelength, the highest frequency, and the most energy, okay? The most energetic, just like the gamma ray astronomers. Okay, so they come from the most extreme places in the universe. For example, they come from black holes in AGN. They come from exploding stars, supernovae, pulsars, and so on. Okay, and observing gamma rays, which is what I do, helps better understand how the laws of physics work in these extreme environments. In these extreme environments, in the distant universe, observing gamma rays helps us understand the physics going on in these places, which to me just sounds remarkable, and that's why I do it. Furthermore, you might remember I mentioned cosmic rays a few slides ago. Also, gamma rays come from the same place as cosmic rays. So locating the source of the emission is quite important, because if we know the source of the gamma rays, we can then go, hang on, that's where the cosmic rays from, and then study those, and then end up making further more conclusions on cosmic rays and the start of the universe. That to me is incredible. So that's gamma rays. How do we observe gamma rays? Okay. To observe gamma rays, what I do is I look at data from NASA's Fermi Large Area Telescope. That's it on the right, on the top, that's what it is. And the inside looks like what's down below. I'll come on to that in a bit more detail now. So it's a pair conversion telescope. So what that means is hopefully you can see an animation. You have the Fermi out over there. Soon we'll have a photon striking the top. So wait for it. Photon hits, forms an electron-positron pair, which then goes on through the telescope. So that's what happens. So gamma rays, they interact with matter and they form an electron-positron pair. Okay, now these electron-positron pairs then also give off more photons. I'll come on to that in a few slides' time. So basically what happens is from one single gamma ray, you get more electron-positron pairs, which then form more photons, and from there you get more electron-positron pairs. So you get like a cascade effect, which I'll explain in a lot more detail in a couple of slides. But basically from single gamma ray, you get an entire air shower of secondary particles. And this is where Fermi comes in, because it's got different bits. You've got the tracker, and at the bottom you have the calorimeter, which measures the energy deposited from this air shower, and therefore by measuring the energy of these particles, you can by proxy measure the energy of the incoming gamma ray, which, you know, to me just sounds remarkable. Now, so the NASA Fermi Lab is quite incredible because it does a full scan of the sky every 3 hours. So every 3 hours, it just basically sees everything there is to see. And this data is made available to the public within 24 hours, usually. So people like myself can play around with it and do interesting things with it. I say usually because now and then, as you might know, the American government go on strike, and let's not go there, but they make the lives of me very, very difficult, because there are bits of life and I don't have any data, bits of the month, and then that just ruins everything. Oh well, never mind, I'll leave it there. Okay, so what do I do with this data? So what I try to do is I try to locate the source of the emission. So I look at these really cool objects. They're called flat spectrum radio quasars, or FSRQs for short. Okay, so they are a subclass of blazars. So blazars, you might know, are AGN with their jets pointed towards us. They come in two flavors. You either get BL lax, which are weak or no emission lines, or you get FSRQs, which are strong, broad emission lines. And I look at FSRQs. I look at them because gamma ray observations have revealed extreme flares, extreme periods of high emission from these FSRQs, and make them really interesting. And yet, despite this, the location and the mechanism for this emission is still unknown, and one of the most active areas of research. So people like me, that's what we look into. There are two main theories. So I refer you to this diagram over here. So this is what a typical AGN looks like. This is the Urian-Padovani scheme, if anyone's interested. So you have at the center, you have the black hole. Surrounding it, you have the accretion disk. Around the accretion disk is the broad line region, the jets coming out, and further away is the obscuring torus, or what I'd call the molecular torus. So there are two main theories. They think the emission is either coming from near the black hole in the broad line region, or from further away beyond the molecular torus. And that is where I come in, because my job is trying to figure out where exactly it comes from. So how do I do this? Well, this is how I do this. So firstly, there's no direct way of doing this, okay? As I mentioned before, these jets are pointed towards us. So imagine someone points a flashlight towards you. You basically have no idea what's going on behind. So that is why what we do is we look at the data and look for little clues, and then we sit back, put them together, and see what bigger picture they tell us. Okay, so I'll give you an example. On the top left is 3C454.3, which is the brightest FSRQ out there. Okay, it's really bright. So that is data from 8 years worth of observation. Now, what I do is I look at the entire data set and I look for periods of high activity, also called flares. So you can see typically you get periods where it jumps up and then down, jumps up and then down. And these are called flares, and I look into them. Now, these periods, because of the more emission, should hopefully provide sufficient statistics for me to then make conclusions regarding the source of the emission. So that is why I look at flares, because they are the best statistics available to study them. Now, for instance, if I looked at this particular flare, so this particular flare happened in November 2010. Now, what I do is I look at the data And then I look at it in more detail. So as I said, this was in monthly bins. I look at it in more finer bins. This is every 3-hour changes in the data. As you can see, the flare, it starts off small, shoots up, and then goes down, and you have a bit of flickering at the end. So what I do, I look at the data, and on that data, I do different fits and try to find the variability timescale. So I do a fit, find the doubling and halving timescales, the quickest variability timescales, and from there, see what that tells me of the size of the emission region. Give you an idea, short variability timescales generally indicate a compact emission region. So small things move or change quicker. That's sort of the idea. So you can relate the timescales directly to the size of the emission region. That tells you the size. Now, to make conclusions regarding the location, which is what I'm after, I make an assumption. Okay, see, most of physics we have assumption. So in this case, we make the assumption that the entire width of the jet, so imagine my hand's a jet, is responsible for the emission. And therefore, the most compact region is down there near the black hole. So if I do see short variability timescales, this indicates the emission is coming from the most compact regions near the center, which is where the broad line region is. This is just an example. They're not always like this. In most cases, they're not. In most cases, they never tell a consistent story, which makes my life annoying, but never mind. Okay, this is one of different ways we do it. So one is variability timescales. We look at things like the spectrum. We look at the spectrum and see if the spectrum tells us about the emission. Does it have cutoff? Does it not have cutoff? We look at the cooling timescale, see if they relate, do cross correlations. But I don't want to get into too many details of that. If you are really interested, do keep an eye out. I have published a paper at the monthly notices of Royal Astronomical Society, which should be out next month. And that's basically my entire PhD thesis. So it's 26 pages of me rambling about where I think the emission is coming from. As I said, I'm not going to go into too much detail. Do ask me further questions if you're interested later on, either after the talk or privately later. Something else I do is I look at the very high energy emission. Let me define this. Very high energy photons for me is anything over 20 GeV. I think that's quite energetic. Now, very high energy photons are in general difficult to explain if the emission comes from the inner region of the BLR. Let me explain why this is. So in the inner region of the BLR, you have loads of other photons. So it's quite dense. Now, the gamma ray photons interact with these other photons and then produce electron-positron pairs. It's called pair production. Photon, photon, pair production. And because they produce electron-positron pairs, it finds it difficult for these gamma rays to escape. And the more energetic the gamma rays, the more difficult it is for them to escape. So basically, if we are observing very energetic photons, that means that they can't be coming from too near the black hole, because black hole, you find it very difficult because there's more place for them to interact with and get attenuated by. So that's what else I look into. So look for evidence of very high energy emission from these sources. The problem is Fermi is not very sensitive at really high energies. So beyond a certain point, on the top you can see loads of photons, but down below, the other source, CTA102, has only 2 photons. And if it's got only 2 photons, it's very difficult to make much sense of it. Okay, now here's the thing. The problem is, of course, Fermi isn't that big. There's only a limit on how big of a detector we can put up there, because we have fuel expenses. We need to be sure. Just putting it out there is difficult. It's impractical to have an infinitely massive detector out there. But if only we had a much larger pair converter detector out there, if only we had such a thing which would do this for us. Well, luckily, we do. It's called the atmosphere. It's all around us. You might have noticed it this morning or throughout your lives. The atmosphere itself is a pair conversion telescope. So what happens is the gamma rays strike the top of the atmosphere and get converted to an electron-positron pair. So, as I said, gamma rays strike with matter, getting converted to electron-positron pair. Now, the next step. You might have heard of Bremsstrahlung emission. So when a charged particle moves in a magnetic field, it gets deflected. And when it gets deflected, it emits extra photons, right? It emits a photon. So the original gamma ray would give an electron-positron pair, which themselves get deflected and produce more photons, which themselves can produce more electron-positron pairs. And that, ladies and gentlemen, is how an air shower forms, okay? A gamma ray, single gamma ray, gives rise to an entire air shower. Now, sometimes these shower particles move faster than the speed of light in air, not vacuum. I said nothing moves faster than the speed of light in vacuum. That's true. But air, it's got a different refractive index. So it is possible for these particles, electrons and positrons, which are quite fast anyway, to move faster than the speed of light in air. And when they do, they produce something called Cherenkov radiation. So on the right is Cherenkov radiation when done in water. To understand this, you might have heard of a sonic boom. So when an object moves faster than the speed of sound, it produces a sonic boom. Similarly, when an object goes faster than the speed of light in air or whatever medium, not vacuum, never happens, it produces Cherenkov radiation. So you've got the radiation. Now all we need is a telescope. Now, we're human beings, right? We're human beings and scientists. We have a problem, we find a solution. We need a telescope, we build a telescope. Not just one telescope, multiple telescopes, an entire array of telescopes. Ladies and gentlemen, I present to you the Cherenkov telescope array. So this is the next generation of ground-based telescopes in gamma ray astronomy, as you can see over here. There will be two arrays, one in the northern hemisphere at La Palma, the Canary Islands. Some of you might have been there, it's very beautiful. The other will be in the southern hemisphere at Paranal in Chile, which is where the current European Space Observatory is. And together they will complement each other because one in the north, one in the south, to provide a full sky coverage. Furthermore, there will be telescopes of three different sizes. So there will be small size telescopes, medium size telescopes, and large size telescopes. And if you're wondering why we need these telescopes of different sizes, it's because of the air showers. So you have an energetic photon, the showers will be spread out more over a larger area. So instead, you need loads of small telescopes to detect these photons. If it's a less energetic photon, the air showers will be spread out over a smaller area. So you need a couple of medium or even large size telescopes to detect it. So that is why we have telescopes of different sizes. Now, the CTA is not yet in operation. It will be in operation in a couple of years. But until then, for some reason, and I don't know what reason, I don't think it's a good idea, they've asked me to make detection forecasts for the CTA. So basically, what part of my job is to predict what sources in the sky we will be able to see with the CTA. I know, I'm not a fan of it either. So what happens is we start off with the Fermi data. Remember, we spoke about the Fermi Large Range Telescope. We start off with the Fermi data. We then extrapolate it to higher energies, so CTA energies. So we put in the numbers into the equations, extrapolate to higher energies. If you want an idea of the energies, they go from 30 TeV to upwards of 200 TeV, so quite energetic. And then my job is to do simulations based on the telescope response. So they're giving me an idea what the telescope should measure. And based on that, my job is to do simulation and predict which sources we should be able to see and come up with a list of promising sources along with the significance of detection, so they can then plan their surveys. So basically their surveys, for some strange reason, rely on my simulations. The good news is it won't be built for another couple of years. So hopefully by the time we do their surveys, I will have finished my PhD and will be long gone, so they can't hold me accountable for all their hours wasted looking at the wrong part of the sky. However, talking about my results, so I don't want to get into too much detail about these plots because they get a bit technical. To give you an idea, on the bottom left, is a histogram of the number of sources against redshift, where all the simulated sources are in blue and the detected sources are in red. So for this particular, which is for CTA South, the one in Chile, at an energy threshold of 100 GeV, we simulate 984 sources, and I expect them to detect upwards of 300, which is 304 sources. That's what I predict. I'm not sure it'll be correct, but that's what I predict. Now that's interesting. That's interesting because currently, for this particular thing, we only see 50 sources. So it shows you the power of the CTA to see many, many sources than we already do. Therefore, the power of the CTA to improve our understanding of the sky will look like. And on the right, you can see the detected sources. So from the entire sky, the colored ones are the ones I predict we will see, where the color corresponds to significance, so how bright it is. So most of the sources I'm predicting will be relatively bright, but you also get some really, really bright sources out there. So that's probably how they're going to plan their surveys. I'm going to tell them, look at that, and they do, look at that, and they do, and I'm going to give them a list of sources so they can then work on. But hopefully, as I said, I'll be long finished my PhD, so I shan't be held accountable for these invariably wrong predictions. So, try and move on with the water. So, as I said, you can notice on this slide that we are starting off with Fermi data. So we are starting off with what we know and then building what comes after. And that takes me to my final slide. Yay, we made it. Well done, people. Okay, with all this in mind, we have reached a crucial point in our explorations in space, okay? The key lies in asking questions, okay, asking loads of questions. Now, I always tell my tutees to ask questions, and they do. I love them to bits. So always ask questions. There's no such thing as a silly question. If something doesn't make sense, just ask why it doesn't. Try to make sense of it. Okay, now all these discoveries are shaped by the past and creating the future, which you might recognize is the motto of our great university: shaped by the past, creating the future. And that's basically what astronomy is, because every discovery in astronomy depends on what comes before it. It's premeditated by what comes before, and also dictates what comes after. Basically, we are shaped by the past, and we are, quite literally in this case, creating the future, which to me is incredible. As I showed you on a timeline, without Copernicus, there wouldn't be Galileo. Without Galileo, there wouldn't be Herschel. Without Herschel, there wouldn't be Einstein. Without any of them, there wouldn't be Atreya, whoever he is. So basically, everything depends on what comes before and affects what comes later. And the really cool thing is you guys don't need to be an astronomer to appreciate astronomy, which to me is remarkable. You know, it's like you don't need to be a musician to appreciate music. You know, we all have our Spotify playlists, which we are all secretly proud, but always a bit nervy about showing other people about. So similarly, let's say that in astronomy, you don't need to be an astronomer to appreciate astronomy. It's out there for all of you guys. In fact, you guys, not me, you guys, based on what we learn at school and what you've learned in university so far and will learn in university, you guys could give Galileo a tutorial. Not me, you guys. And that's the privilege of living when we do now. So Galileo was a polymath, one of the greatest people who ever lived, you know, one of my greatest heroes. And yet he lived at a time where they didn't know about motion, they didn't know about exoplanets, and this guy didn't know about relativity. So you guys, based on what you already know and will learn, you guys give Galileo a tutorial, which to me is incredible. Now that brings me to my final point. Okay, and before I go into this point, I'd like to firstly thank Luke, Kiki, and entire Durham University Physics Society exec for giving me the chance, giving this talk. I've really enjoyed it. Thank you so much. I'd like to also thank them for all their communication and the incredible job they're doing, in these difficult times. So thank you so much. Hats off to you. I'll also thank them and Sarah as well for her communication, organizing this thing. So thank you, Sarah. So part of what we did before is we had that video, we put it on Facebook. You might have noticed it, I don't know. I never done all these videos before. So when they asked me to do it, I was a bit nervous. So I sat outside and did a video. And I don't even know if it was any good, but I don't know. It's not got viral yet, but I don't know. There's still time to get it viral. Get me a job at the BBC. But I really enjoyed it. So thank you. And there are going to be loads and loads of brilliant talks to follow. So loads to look forward to. Okay, now the reason I mentioned this last one is in the video, I spoke about exploring space, because here's the important thing. Okay, as I mentioned in the video, when we look out in space, what we're actually doing is looking back in time, looking back at history. And I'll tell you why that's important. Because everything, all of us, everything that makes us, everything around us came from the Big Bang, So when we look out at history, it's not just any history. What we're actually seeing is my history, your history, our history. So when we explore space, we're actually seeing our own history, where we come from. History before history was invented, which to me is absolutely incredible. And this is why I love doing astronomy. So by all means, when you're going out this evening, when you do see the sky, do look up, see the stars, see the galaxies out there. There's really an entire universe to explore. You don't need to be an astronomer to do that. So keep on going. All the best what lies ahead. I'll end you with this. We're astronomers. This is what we do. Someone's got to do it. I definitely need you. Thanks for listening. It's been my pleasure.